Hello, welcome for this e-lecture about the design of cold form profiles. This work is funded by the RFCS in the field of the CRISPR+ project. Now we are in the module 1. During this module 1, we will study the technology and the principle of a cold formed element. We will study also the different types of cold formed elements, how to manufacture a cold formed element, how to use the cold formed element in construction, the different European standards concerning the materials and the cold form profiles, the different profiles studied during the CRISPR project. We will see also the different methods to design a cold formed element. We will see the different tests to study a cold formed sheeting. And finally, we will see the different collapses and anti-stabilities of the cold formed elements. Some words to calibrate to present this e-lecture. First, the present material complies with the current version of the Eurocode 1993 Part 1.3 and 1993 Part 1.5. The amendments proposed by CRISPR+ are not taken into account in this presentation. For this, it will be necessary for you to go at 9 other e-lectures that will explain you in detail how to design these profiles. This training is an initiation to the design of cold form profiles. Some simplifications are provided to help the learner. In all the cases, it is necessary for you to refer to the original Eurocode to have all the clauses that must be applied. In all the cases, you have to take into account of the national annex of each Eurocode. This material does not cover assemblies that also have to be checked. For that, it is necessary to see the EN 1993 Part 1.3 and the EN 1993 Part 1.8. So this e-lecture is a transversal e-lecture that will help you to understand the behavior of a cold form profile, how they can be tested, and you will see how to design these profiles. Okay, now we are going to study the principles of the cold form elements. You can see that in fact there is 4 main principles. First, it is necessary to optimize the material. Secondly, it is necessary to find inertia to give ribs to the elements. It is necessary to add stiffeners to avoid local instability in the compressed area. And sometimes you can add embossments to facilitate the liaison concrete and steel. So I come back to the first. Optimize the material with thin metal sheet. You can see here a picture with some coils. The thickness of the raw material is around 0.5, 0.75 millimeters. So it's very, very, very thin. As it is done in the nature, as you can see of this figure on the shell, you can see that some ribs are added to give a good inertia and a good resistance of the shell. It is the same principle that is used for the cold form profiles. We add the ribs to give inertia and resistance of the profile. As we have very thin sheet material, the cold form profiles are very sensible to the compression. That's why it is necessary to add a stiffener, and you can see here on the 2 first pictures some stiffener put on a flange, and on the right some stiffeners put on the web of the profile. The last point, you can see that the concrete has a very good resistance in compression. The steel has a very good resistance in tension. So it is interesting to add these 2 characteristics and to create a composite system. We obtain a composite floor, for example. Here, to obtain this, it is necessary to block the slipping between the steel and the concrete. That is why some embossment or indentation are added in order to block this slip and to create a composite system. Okay, now we know the principle of the cold formed elements. Now we are going to study the different types of cold formed elements. You can see that in fact there is 2 families of profiles. The sheetings that can be used in cladding, roofing, covering, decking, or members that can be used in purlin, column, cladding and rail. On this figure that you can find in the Eurocode, you can see on the left some sheetings that can be used to carry out cladding, roofing, covering or decking. And on the right, you can see that there is some purlin with the shape of Z, sigma, that are very current. So 2 families of profiles, the sheetings, the members. Now we are going to study how to manufacture, how to carry out these cold form profiles. In fact, it's very simple. You have to use a profiling machine. You put in this machine a coil, and you have a series of rollers that give, step by step, the shape of a profile. You can see on the left an example of this profiling machine, and on the right, the different set of rollers that give step by step the shape of the profile. Okay, now we are going to study where are used these cold form elements. The first use could be the cladding. And here you have 3 examples of use of cold form profile in cladding. In the first, you can see that the cladding is laid with vertically ribs. You can see the frame, the horizontal purlin, and the cold form element fixed on this purlin. It is a single skin system. For the 2 others, you can see that layers of insulation are added. This is carried out to be sure that we respect the thermal regulation. In fact, we increase the resistance, the thermal resistance of the system if we add layer of insulation. On the left, it's a facade cladding. The existing wall is in concrete. On this wall, we go to fix spacer, and we fix after the external sheet. And between, we have a layer of insulation. On the right, it's a double skin system. The first skin can be carried out by liner trays. After, you have spacers, and this spacer can have a distance between them of 1 meter, 2 meter, 3 meter. We will see later that it's very important to take into account of this distance. We have layers of insulation, and at the end, we have the external skin. So the cladding is the first type of use of the cold form profile. The covering is the same principle. You can have a single skin covering, or you can have a double skin covering. For the single skin covering, again, you have the frame with purlin. After, you have the profile sheet. After, you have saddle washer that fix the profile sheet on the purlin. On the right, you can see a double skin system. Again, you can have a first skin that can be made in profiles or liner tray. After, you have layers of insulation. After, you can have spacers, and after, you can have external sheet. Okay, so 2 families, the single skin covering, the double skin covering. Another use concerns the roofing. It's a very easier system. Again, you have the frame, the 2 purlin, you have the cold form profiles, you have the layer of insulation, and finally you have a membrane, a water tightness and water tightness membrane. This water tightness membrane avoids the problem with water. This system is very interesting because you can increase the thickness of the insulation as you want. Finally, you have the last category, that is the composite floor. So you have the cold form element, you have the concrete that work with the steel, and you obtain this decking and this composite floor. Okay, now another use of the cold form profile. Now we are in the frame, directly on the frame of the building. On the left, you can see a portal frame made with cold form elements, and you have on the right a zoom of the assembly and a zoom of the portal frame. Here you have some details about the purling and the cladding array made with the members. Okay, now we are going to study the European standards for cold form elements. We have 3 standards, the EN 10143, the EN 10346, and the EN 10169 plus Amendment R1. The EN 10143 concerns the tolerances and the metal core. The EN 10346 concerns the protection against the corrosion made with metallic coating. The EN 10169 plus Amendment A1 concerns the protection against the corrosion carried out with organic coating. So these 3 standards concern the raw material. After, we have a CE marking of a product, and we have a CPR, the Construction Product Regulation. It's a regulation, so it's obligatory, mandatory in each country. We have 2 families, for non-structural products and for structural products. For non-structural products, we have 2 standards, the self-supporting standard, EN 14782, and the fully supported standard, EN 14783. How to use these standards? If the span of a profile is inferior to 400 millimeters, you have to apply the fully supported standard, the EN 14783. If the span is above 400 millimeters, you have to apply the self-supporting standard, the EN 14782. These products are in class 3 for non-structural use. That means that the product transmits only the load on its support. The EN 508-1 is useful to determine the measurement and the protection phase. For structural product, we have to apply the EN 1090-1. We have 2 categories, class 1 for the diaphragm use and class 2 for the collaboration between the member and sheeting. The diaphragm, you have this system when you use the cold form element to stabilize the construction against the wind and against the earthquake. The class 2, it is used when the profile collaborates with the members. Okay, it's the shear marking. Now the design and the erection of a system and buildings. You have the design test and calculation, and for that you have to apply the Eurocode. You have 3 parts of the Eurocode, part 1.3, part 1.5 and part 1.8. Part 1.3, its corrigendum and its national annex concern the general design. Part 1.5 plus its corrigendum and national annex concern the effective width. The part 1.8 concern the assemblies. So 3 parts of the Eurocode EN 1993. For the building erection, you have to apply the EN 1090-4 for the steel products. Okay, now we are going to study the profile steel sheeting covered by the GRISP Plus project. The first family is the decking with embossment and or indentation and the decking with outside stiffeners. Indeed, this profile are covered by the Eurocode, but you can only design this profile by testing today. You have no method to calculate this profile. That is why, during the GRISP project, different methods were proposed to calculate this profile, how to take into account, in fact, the embossment and the indentation in the calculation. The same thing was done for the decking with outside stiffener. And here you can see a diagram of stress that explains which stress must be taken into account. So the first part of GRISP, how to calculate, how to take into account the embossment and indentations. Another topic of GRISP was the liner trace, and especially the distance S1. You remember, some slide before, I explained you that due to the thermal regulation, we add spacers between the liner tray and the outside skin. This spacer, the distance between these consecutive spacers can be 1 meter, but can be 2 meter, 3 meter, 4 meter, to avoid thermal bridge. But when you do this, you have a local instability of the flange of a liner tray. That is why it is necessary to take into account this in the calculation. It is not defined in the Eurocode today. It was developed in the Eurocode in the future, thanks to the work of GRISP. Another topic concerns the corrugated profiles. You have here some example of corrugated profiles. Again, no methods exist in the Eurocode to calculate in bending these profiles. 2 methods were proposed in the European project GRISP to calculate. One is forfeiture, another is calibrated in detail. Another topic concerns the curved profile, and you have 2 families again. You have the curved profile. When you put this profile on the work site, the profile takes naturally the shape of the structure. It's the first categories of calculation of profile that don't exist in the Eurocode. Another solution, you pre-curve the profile in manufacture, and this profile is transported like that and put on the work site like that. And in function of the support, you can have a horizontal support or block support, you can have an arch effect or no arch effect, and no calculation method exists in the Eurocode. For these 2 categories, a new system, a new approach was defined and will be in the future in the Eurocode. Now the assemblies. You know, sometimes for the work site, we need to have profile of 20 meters, for example. Of course, it becomes difficult to transport this type of profile of 20 meters. For that, the profiles are cut in 2 parts of 10 meters, for example, and reassembled on the work site. But to do this, you have to calculate this assemble, and it is not defined in the Eurocode. That is why, in the GRISP project, 4 types of assemble was studied. In the first, the cantilever above profile, you can see that the profile on the left is above the profile on the right. For the cantilever underneath, you can see that the profile on the left is under the profile on the right. We have another type, the overlapping joints. In this case, the overlapping is symmetric. You can see a vertical axis in front of the central support. And finally, we have a continuous profile with a local reinforcement. So a piece of metal is added to reinforce the structure and the sheeting on the support. So 4 types of profile, 4 types of assemblies. To do that, 4 tests were done. The first test was done on continuous profile that served of reference, and 3 other tests were done about the DIN overlapping, about a 2-slided overlapping, and the continuous profile with reinforcement to obtain data to calibrate the design method. Another topic concerns the acoustic. Due to acoustic, it is interesting to create perforation inside the cold form profile. This perforation can be on a triangular shape or a square shape. The problem is that on the Eurocode could cover today only the triangular shape and not the square shape. That is why this new distribution of the perforation was studied in the European project GRISP+. Another topic concerns the services. Some tubes can go through the profiles and create hole, circular hole or square hole. Again, no method, no design calculation will exist in the Eurocode, and it was developed in the European project GRISP. The last concerns the Planck profiles. These profiles are requested by architects that want to have facade without visible fasteners. You can see here two types of clip joint and chevron-shaped joint that allow to hide the fastener. The problem is when you do this, you have a specific value that is named is dislocation that don't exist in the Eurocode. That is why a new method was proposed to calculate this assembly in the Eurocode and to calculate also the Planck profiles. Okay, now we are going to study the method to design a cold-formed element. We are, in fact, three methods to design a cold-formed element. You have the design by calculation, you have the design by testing, and you have the FEM designing, finite elemented models. About the design by calculation, it's very simple. First, the formula exists. They are defined in the Eurocode. So you go in the Eurocode, you check first the application criteria of the formula. If the check-in is OK, you can apply this formula and find your result. The problem becomes when it is no. In this case, you have no choice. You must make a design by testing. What is a design by testing? First, you have to carry out a test program. In this test program, you will define the geometry of the profile, the number of end support tests, the number of bending tests, the number of interaction, bending moment, resistance of support tests, and end coupon test. When you have done this, you carry out a test report. In this test report, you will describe Fy, that is the yield strength of the profile, Fu, that is the ultimate stress of the metal used for the profile, Tops, the thickness of the system. You will obtain some curve, load displacement, and some type of collapse. When you have done this, you can make test interpretation. In this step, you will determine, by a statistic approach, the bending moment resistance, MRD, the shear resistance, VRD, and the reaction to support resistance. And you will propose a curve interaction, MR. With all these elements, now we are ready to build a design formula. And again, you have two choices. You can put this formula inside the Eurocode, and you are now in the design by calculation, or you can make an Excel software. In fact, GRISP made this approach. We make tests, we apply the design by testing in view to propose formula that will be included in the future in the Eurocode via amendment. Now it remains the FEM designing. It's difficult to use it because we have cold-form elements very sensible to local buckling. But it's very useful to make interpolation between tests or to develop new tests or develop new profile to avoid a number of tests too much important. And what is done after, you can again make design by testing and design by calculation. Okay, now we are going in detail to the test program and to the design by testing approach. Now we are going to study the test to study the cold-form sheetings. The first step, the vacuum chamber. The principle is very simple. First, you have a frame support. You put on this frame support a profile sheeting. You put on the profile sheeting a water and air tightness membrane, and you create a suction under the profile. You measure the reaction of the support, and by this way, you know the load that is applied to the system. On the right, you can see a real test setup carried out at the laboratory KIT in Germany. The objective of this vacuum chamber is to determine the effective inertia of the profile, E effective, and the bending capacity, MCRD. Now we have an example of curve load displacement and an example of curve load displacement concerning the reaction of the support. On the right, you can see a test result and the typical failure of the dislocation of the plank. The main collapses what we can see are the download below download pressure, buckling of the compressor facing, and upward load, suction, dislocation of the profile assembling. These two main collapses are seen very correspondent. The single pan bending test now. The objectives of this test are to determine the effective inertia of the profile, E effective, and the bending capacity, MCRD. So it's exactly the same objective that previously. But in this case, the load will be applied by linear loads. In the previous test, the load was uniform by vacuum chamber air. Here you can see a global setup of this test. You have an arrow that represents the jack. You have a frame that is transmit the load on the profiles with hinges to be sure that the repetition of the load is divided by 4. You have the profile, you have the supports, and of course the profile is never fixed on the support in the test of the Eurocode. And you have in red a sensor that allows to measure the displacement. By this way, we will have a relation between the displacement and the load applied on the system. Again, you can see the setup on the left, and on the right, you have a real situation where you can see on the top the jack after the frame. You can see the hinge, you can see the liner bar that transmit the load on the profile, and you can see several pieces of wood that transmit the load on the profile. An important point, you can see that on the support, some pieces of wood are included. This, it is done to be sure that we have no collapse on the support, and we will have a collapse in span because the objective of this test is to determine the resistance in span and not on the support. Now we have an example of curve load displacement. You can see that the curve that we have on the left is linear at the beginning, and we have a curve at the end. The linearity at the beginning is a proof that the system has an elastic behavior. At the end, you have a plasticity, and we obtain the ULS load. It is the collapse load. It is the maximum load that can be applied on the profile. When we load this load, we divided this load by 1.5, and you obtain the SLS load. This SLS load is used to determine the effective inertia of a profile. On the right, you can see some example of buckling, and two cases here, the profile without embossment and the profile with embossment. In both cases, we can see that we have a local buckling in span. Now some example of test interpretation. For example, in the WP1 of the European project GRISP, where we studied this profile with and without embossment, we can see that if we add an embossment, we have a reduction of the bending resistance, a decrease of 10%, and a decrease of the inertia moment of 11%. So add embossment, decrease the strength capacity of a profile. Now another test, the intermediate support test. The objectives of this test are to determine the interaction between the bending moment MCRD and RWRD and the reaction of the support RWRD. Now we have a global view of the setup of this test. Again, we have an arrow that represents the jack. We have a support with in the shape of U. We have a profile, and we have the two supports. Some timber blocks are put on the support, again, to avoid problem of this support and to be sure that we will obtain a collapse in span. Again, we have sensor displacement, but this time we have 3. In the centrum, it is used to determine the curve load displacement. At the end, it is used to determine the rotation of each support. Thus, it will be possible later, during the interpretation of the test, to find a law between the rotation of a profile and the bending moment. On the right, you have an example of a setup carried out on the KIT laboratory. Here now, we can see a curve load displacement obtained with this test, and on the right, a typical collapse obtained with this test. Now, an example of interpretation. This time, it's the WP3 of the European project GRISP concerning the square pattern perforation effect. We can see that if we have a flange perforation only, we have a reduction of the moment reaction interaction of 5%. We can see also if we have a perforation in the web, we have a reduction between 11% and 19%. And if we have a total perforation of a profile, in this case, we have 42% of reduction. Practically half of the resistance disappear. Another test now, the end support test. The objective of this test is very simple. Determine the capacity of the end support reaction, RWRD. We can see two setups. On the left, it is the setup defined in the Eurocode. On the right, it is the setup used during the GRISP project. Why a difference? This difference concerns the piece of wood that are put below the plate where the load is applied. You can see this on the right. These timber blocks are added to be sure that the load is applied at this point, and this facilitates the calculation of the load on the support after. Again, this setup, and on the right, the real situation carried out at the KIT laboratory in Germany. What are the test results? Again, we have a typical curve load displacement. We have 3 peaks this time. A first peak that corresponds to the SLS, a peak number 2 that concerning the ULS, and peak number 3 that concerns the collapse of the profile. On the right, you can see the corresponding situation. Peak 1, it corresponds to the web that becomes vertically, is the figure on the right, on the top. Peak 2, this time you have a completely rearrangement of the profile. It is on the bottom of the figure on the right. An example of in-test interpretation now. For example, in WP1, you can see that the embossment increases the reaction on the support. In fact, the increase is 20%. So, add an embossment, increase the resistance of the profile at the end support reaction. Now we are going to study the collapse and instabilities of the cold-formed elements. As we have seen in the test some slides before, very often a local buckling occurs. For example, on the corrugated sheet, you can see a buckling here. We have the same behavior on a plank on the right. Another example concerns the liner tray. Here it's a global test, and you can see that the top of the flange have a buckling, and we see this also in the figure on the right. Again, a local buckling and a local impression and an intermediate support. You can see an ensemble of profile here, and on the right, a local impression of the wet plus a web crippling area. Another example of local buckling and impression of a support, this time on corrugated sheet. Again, we have a web crippling and in the compression area of the profile. You can see this on the right. Another phenomenon now, the yielding. This occurs very often with corrugated sheet. In function of the shape of the profile, you can have a global plastification of the profile. It's the yielding. Another behavior now, the shear collapse. On the left, you can see the setup of this test, and on the right, you can see the consequences on the profiles. You can see again that we have a web crippling in the shear area. Another example concerns the local web crushing and the web crippling. Here now we have assembly on continuity on support. And you can see on the right and on the middle the web crippling on the overlapping area. Web crippling again, this time with corrugated sheet. Web crippling again with plank profile and on trapezoidal profile on the bottom. Now we study the fasteners in the valley. You can see the position of the fastener on the photo on the right and the consequences of a suction applied on the profile on the left. You can see that in all the area in compression we have a buckling. It's the same situation, but this time the fasteners are put on the crest of the profile. And again, we have a buckling in all the area in compression. Now it's the case of a liner tray. Again, we have a suction applied to the liner tray, and in the flange in compression, again, we have a buckling. Again, we have a view of a dislocation of a plank on the right, and on the left, you can see a very interesting picture because it's possible to see that between the spacer on the liner tray, we have a lateral buckling. And this will be studied with the famous S1 dimension between the spacers. Thanks for your attention, and don't hesitate to go at the next e-lectures.